Hi everyone, welcome back. In this video, we're going to talk about optimization problems. So the general strategy for optimization problems is to set up variables for unknown factors in the question, and then we need to identify what's being optimized in the question. It could be a function, or it could be a single variable. And then we need to find respective local extrema for certain functions that's being represented in the stem of the question. And the key for doing so is to find when the derivative of the function that we're trying to look for local extrema is equal to 0. And the reason being is as illustrated in this diagram. So as we can see, if we're looking for a local minimum on a function, the derivative, which indicates the slope of that particular point, the instantaneous rate of change of that point, must be 0 for local extrema and local minimum and local maximum. As you can see, if you're looking for this point or this point, this is a local max and this is a local min. Both of them will have a slope of 0 when we draw a simple tangent line for these 2 points. So since these 2 lines are both horizontal, so their slopes must be 0. Therefore, the derivative for either one of them must be 0 as well. And the next step in solving optimization problem is to bring it back into the context of the problem and to see whether the local max and min satisfies what we are looking for specified in the stem of the question. And finally, problem solved. So these the above are the general strategies for solving optimization problems. Of course, different questions will have different strategies, and it's a case-by-case scenarios. And we're now going to look at 3 typical examples that are usually being tested for optimization problems. Example number 1. Find 2 positive numbers whose product is 100 and whose sum is a minimum. So first, we need to set up variables for unknown factors in this question. So as we can tell, the unknown factors in this question are the 2 positive numbers. So we can say, let x be one of the numbers. And since the product of the 2 numbers is 100, then the other number must be 100 divided by x, which is 100 over x. So we can set up a function representing the exactly thing that we're trying to optimize. So as we can see, the question specifies we need to look for the numbers when their sum is a minimum. So we must set up a function representing the sum such that we can optimize the sum, which is the function itself. So we can say fx, which will be sum of the 2 numbers in this case, will be equal to x plus 100 over x. So this would be the function that we need to use to perform the optimization, which to find when the derivative of this function is 0. So the next step is finding the derivative of this function, which is f prime x, because we know that this fx must have some local extremas, and we're trying to find the local minimum of this function fx, which will give us when the sum is a minimum. So the derivative of this function, if we use derivative rules, we will find that it is 1 minus 100x to the power of negative 2. And if we write it in a nice way, it's 1 minus 100 over x squared. And next is to set this derivative as 0 because we're trying to find local extremas. And then we will have 1 minus 100 over x squared is equal to 0. And we will have 100 over x squared is 1, x squared is equal to 100, and x is positive negative 10. So logically speaking, we already found the two numbers or the values for x that could satisfy the condition of the question where the sum of the two numbers is a minimum. However, now we need to go back to the context of the question and see whether these two numbers of x actually satisfy the question or not. And we can see that the question specifies that the two numbers are both positive, therefore x cannot be the negative 10. So x can only be positive 10. So the one of the number is 10 and the other one is 100 over x. So 100 over x is 100 over 10, which is 10. So the two numbers are actually identical, 10 and 10. And this question follows perfectly through our general strategies that we talked about before, earlier in this video. Next example, example number 2. Find the dimensions of a rectangle whose area is 8,000 centimeters squared and whose perimeter is as small as possible. So first, we still need to set up variables for any unknown factors in this question, and we can see that the unknown factors in the question are the dimensions of the rectangle. So we can say let L be the length of the rectangle, then the width is 8,000 over L. Next, we need to find the exact thing that needs to be optimized. In other words, needs to be figured out the local extremas. So that piece of information in this question would be the perimeter. So we can set up a function for perimeter. We can say P of L is equal to 2 times length plus width, like this. And then, in order to find the local extremas, we still set derivative equal to 0. So the derivative of this function is 2 times 1 minus 8,000 over L squared, excuse me, which is equal to 0. And if we solve this equation, we will get L is actually equal to its 40 root 5. So that would be the length of this rectangle. And since the question is asking for dimensions, we will see that the width 8,000 over L is equal to 8,000 over 40 root 5, which will give us 40 root 5 again. And the units are centimeter. So therefore, the dimension of the rectangle will be 40 root 5 times 40 root 5 centimeter. And so this is how we can solve this question, this optimization question. And the general strategy still follows through. And when we set the derivative is equal to 0 here, this is saying that the perimeter, we are finding the local extrema for this perimeter. And this is where the local minimum lies. And this aligns perfectly with the stem of the question, where it asked explicitly for when perimeter is as small as possible. So these are the two very typical examples that you can see that our general strategy for optimization questions follows through very nicely and smoothly. I hope this video is helpful, and thank you for watching.